Hello, my name is Madina and this is my project for 2D computer animation. And my today's topic is HUMANEVE, Synchronized Video and Motion Capture Dataset and Baseline Algorithm for Evaluation of Articulated Human Motion. So let's get started. I want to introduce a dataset for evaluation of human pose estimation and tracking algorithms. This is a comprehensive dataset that contains synchronized video from multiple camera views associated with 3D ground truth, quantitative evaluation measures, and a baseline human tracking algorithm. All the data and associated software is made freely available to the research community. So, hope that this dataset will lead to further advances in articulated human motion estimation, as well as provide the means of establishing the state-of-the-art performance of current algorithms. Despite the fact that the recovery of articulated human motion and pose from video has been studied extensively in the past 20 years, quantitative evaluation of human pose estimation and tracking is currently limited due to the lack of common dataset containing ground truth with which to test and compare algorithms. Instead, qualitative tests are still widely used and evaluation often relies on the visual inspection of results. This is usually achieved by projecting the estimated 3D body pose into the image. To achieve ground truth, previous approaches have resorted to custom action-specific schemes. Alternatively, synthetic data have been extensively used for quantitative evaluation. While synthetic data allow quantitative evaluation, current datasets are still too simplistic to capture the complexities of natural images of people and scenes. For 2D and 3D methods, no standard error measures exist, and the results are reported in a variety of ways which prevent direct comparison. For example, normalized error in joint angles, joint center distance, and etc. Here we describe two datasets containing human activity with associated ground truth that can be used for quantitative evaluation and comparison of both 2D and 3D methods. And I am going to describe two datasets containing human activity with associated ground truth that can be used for quantitative evaluation and comparison of both 2D and 3D methods. Solutions to articulated human motion estimation fall into two categories: pose estimation and tracking. So, pose estimation is usually formulated as the inference of the articulated human pose from a single image, and tracking is formulated as inference of the human pose over a set of consecutive image frames throughout an image sequence. Tracking approaches often assume knowledge of the initial pose of the body in the first frame and focus on the evaluation of this pose over the time. Tracking and pose estimation can be performed in 2D or 3D. In each case, the body is typically represented by an articulated set of parts corresponding naturally to body parts, for example, limbs, head, hands, feet, and etc. To simultaneously capture video and motion information, subjects wore natural clothing on which reflective markers were attached using invisible adhesive tape. It's unusual because tight-fitting motion capture suits, as you can on the screen the example, typically used for pure motion capture sessions. Motivation was to obtain natural-looking image data that contained all the complexity posed by moving clothing. One negative outcome of this is that the markers tend to move more than they would with a tight-fitting motion capture suit. As a result, the ground truth motion capture data may not be as accurate as that obtained by more traditional methods. As a result, in the cases when motion capture data for some frames in some sequences are missing markers or inaccurate, they are excluded from the quantitative comparisons. Markers are often barely noticeable at video resolution and hence will likely have an insignificant impact on the performance of image-based tracking algorithms. Since all the data was captured in a laboratory setting, the sequences don't contain any external occlusions or significant clutter, but don't exhibit the challenges imposed by strong illumination. For example, strong shadows that tend to confuse background subtraction. Even at 60 Hz, the image still exhibits a fair amount of motion blur. So, HUMANEVE-1. HUMANEVE-1 contains data from 4 subjects performing a set of 6 predefined actions in 3 repetitions, twice with video and motion capture and once with motion capture alone. HUMANEVE-2. HUMANEVE-2 contains only 2 subjects performing an extended sequence of actions that we call combo. In this sequence, a subject starts by walking along an elliptical path, then continues on to jog in the same direction and concluded with the subject alternatively balancing on each of the 2 feet, roughly in the center of the viewing volume. You can see photo examples on the screen, starting from walking, then jogging, then balancing. The skeleton of the body is modeled as a 3D kinematic tree with the limbs represented by truncated cones, as you can see on the screen, these cones. And 15 body parts were considered: pelvis area, torso, head, upper and lower arms and legs, hands and feet. There are 2 types of parameters that describe the pose and shape of the body. The shape is given by the length and width of the limb, which in our case are assumed known and fixed. This one. They are fixed. Objective is to recover the pose of the body, which is parameterized by a reduced set of 34. The hips, shoulders, and thorax are modeled as a ball and socket joint, while the knees, ankles, elbows, wrists, and head are assumed to be hinge joints. This one, these small balls. Or this one. So, the subjects in the dataset were all manually measured, but to obtain the height, weight, limb width, and shoulder joint offset. Motion capture training data was then used to estimate limb length for each subject, as well as to learn static and dynamic priors for different motion styles. The raw data consists of the location and orientation of local coordinate systems at each joint. Limb lengths are computed as the median distance between pairs of corresponding joint location over a large set of training motions and are kept fixed during testing. Researchers also derive joint angle limits and interframe joint angle variation from the static of the relative joint angle between neighboring body parts. For each particle in the posterior representation, its likelihood represents how well the projection of a given body pose fits the observed image. Many image features could be used, including appearance models and optical flow constraints. However, most common approaches rely on silhouette and edges. The simplest model applicable to generic motion assumes no change in state from one time to the next. Researchers reject any particle corresponding to an implausible body pose. They check for angle exceeding joint angle bound and producing interpenetrating limb. In implementation, researchers test for intersection between the torso and the lower arms and between the left and right calves. Here is the term action model or AM for filtering and the valid range of the joint angles. Action model can be learned specifically for a certain actor or for a particular motion style, or they can be generic. The training data in the HUMANEVE dataset contains walking, jogging, hand gestures, throwing and catching a ball, and boxing action styles from 3 different subjects. Subset of these were used to learn style-specific action models. For example, for sequences containing both walking and jogging, it's typically for the flexion-extension movement of the elbow to cover the joint angle intervals for the 2 styles. A combined action model for walking and jogging can be learned. Series of experiments were performed with the 2 different algorithms. Most of these are variations of a base configuration. Also, signals where the limbs penetrate each other were rejected. The experiments were conducted on the 2 sequences in the HUMANEVE dataset. To get a measure of performance consistency and repeatability, each experiment was run 5 times for each of the sequences. Authors plot the mean of error measures for each time instant over all the runs, while for the base configuration, they also highlight the standard deviation as a gray overlay. The errors at each frame are combined to compute the average error for each of the 3 activity phases: walking, jogging, and leg balancing, as well as the overall error over the 2 sequences. The computation time is directly proportional to the number of particles, number of camera views, and number of layers used, and vastly depend on the choices of likelihood function. Performing full inference with 1000 particles per frame for 4 cameras views takes about 40 seconds on a standard personal computer with software written in MATLAB. Since walking and jogging are periodic motions, the arms and legs are usually found again during the next cycle. So figure 8 shows that limb extremities are the hardest to track. Large errors for the wrist are obtained when the elbow becomes fully flexed and gets stuck in this position. The result also highlights the relative degree of difficulty of the 2 sequences. They are relatively similar, except for the jogging phase, where the second sequence is significantly more difficult to track than the first and presents larger variances in performance. This is consistent with the fact that the second subject is jogging faster. The 2 sequences contain walking and jogging styles, followed by balancing on the both legs in turn. Training data, however, only covered walking and jogging. So, walking style action model is W, walking and jogging style action model WJ, generic action model with an anatomic joint limit JAJL, generic action model without joint limit is J0JL. Author found that the most accurate results were obtained when the activity matched the style-specific action model used. For example, the walking model W worked well for walking, but not for other activities. The WJ, or walking-jogging, model performed significantly better on jogging, but W and WJ failed to generalize to the balancing style because the joint angle limits were too narrow at the hips and shoulders. However, JAJL, or generic action model with anatomic joint limits, was able to generalize well to each of the 3 different styles: walk and jogging, and balancing, remaining relatively competitive with the style-specific action models. The main computational cost in both the APF and TIR is the evaluation of the likelihood for each particle. We also varied the number of particles used in the baseline configuration. Using more particles helps prevent the tracker from losing track and improves performance. The tracker is much more stable when run using 200 particles. The HUMANEVE 2 dataset used 4 cameras placed on the corner of rectangular area. The results clearly show that monocular tracking is beyond the ability of the present algorithms. Adding a second camera view significantly improved the result, but still the tracker couldn't cope with simple walking motions. At least 3 camera views were needed to track walking motions, and 4 were needed for more complex motions, such as jogging. For walking motions, there was no statistical difference between using 3 or 4 camera views. So, my conclusions. First of all, model. Author's model of the body is an approximation to the true human body shape. They make 2 key assumptions that, first of all, the body is made of rigid, cylindrical or conical segments, and second, joints only model the most significant degree of freedom. More accurate body models may lead to more accurate tracking results, but this hypothesis needs to be verified experimentally. Second conclusion, image likelihood. Based on the observation, researchers believe that one of the key problems in human motion tracking is the formulation of reliable image likelihood models that are general, don't require background subtraction, and can be applied over a variety of imaging and lighting conditions. They have implemented relatively standard likelihood measures. However, other likelihoods have been proposed and should be evaluated. And the last one is fairness. Authors have observed that it's generally harder to track the upper body due to frequent occlusions between the arms and the torso. The upper body also tends to exhibit more stylistic variation across people. The lower body must provide support and hence is more constrained by the dynamics of the motion itself. So here my project is done. Thanks for your attention. And I want to notice that this topic is quite hard for understanding, but I really liked it. For me, it was really interesting, and I tried to do all my best, try to understand and explain as much as possible. So, thank you for your time and for your attention. Goodbye.